Hi, this is a lecture on the direct applications of the class group algorithm. This lecture is a part of the isogeny-based cryptography summer school of Bristol 2021. There are lecture notes that are available in the comment section of this video. Now let's see what kind of applications we're looking at for isogeny. First, we've seen it before in the previous lecture. We want short vectors, so we want to be able to find short vectors that are equal to, so short relations. Also, we want to find solve the more general problem of if you're being given a class which is represented possibly by a reduced quadratic form, we want to express this form as a product of a small number of generators, and if possible with a short vector. And then we want to do these things in suborders of the maximal order. So these are given by a discriminant that is the fundamental discriminant, so that of the maximal order, times f squared, where f is what we call the conductor. So the situation in which we can end up is that when f is large, in fact, because everything is given in terms of d, the discriminant is we've seen in the previous lecture on the class group computation, and we'll see the subsequent problems here also have the same complexity. It's all a function of d, the discriminant of the order where you're working. So it could be that we have the maximal order of very small discriminants, but then the suborders might have a large discriminant because it's multiplied by f squared, where f is potentially large. So we could have easy problems in the maximal order, but they may become very much harder as we descend in suborders. But descending in suborders is sometimes very interesting, particularly because of the volcano structure of endomorphism rings of ordinary curves. So one way typically that is done is with the Bisson-Sutherland endomorphism ring computation algorithm, which requests that we be able to find short relations in the class group of any of the orders that are potential candidates for being the endomorphism ring of a given curve. So this is known to be easy at the top, but is it going to stay easy at the bottom? We'll present here a technique that helps answer this question. So what do we have? How do we reduce the problem of rewriting an element to linear algebra? So what we have at the end of the class group computation is a generating set for lambda. Now we can compute what's called the Hermit normal form, which is a basis of that generating set, of the lattice generating by that set, that has this following shape. So there is a square matrix here, and if n0 is the cardinality of our generating set, then we can guarantee that this size is n0, okay, while n is the size of our larger generating set, the full factor base that has sub-exponentially many elements, why we know that only a small generating set is required, and it's going to have this shape. It's going to have zeros here and zeros there, and then here is going to have a block of elements whose size is going to be balanced. This is going to be triangular, and then the diagonal elements are going to be dominant here. So what is interesting is we can use, so first of all, we have a basis, so that's always interesting, but also we can use that in order to rewrite a given form. So let's say there's a form fi for an I greater than n0, then we can use this information to rewrite any of these fi's as a product of the elements fi for I ranging from 1 to n0. Now, how does that help us decompose an input? So assume that you multiply an input f, which is a reduced form representing the ideal class of your choice, by random products that are correspond to the small generators of your class group until it is smooth. Now, the smoothness probability, and that's really important, the smoothness probability is higher the more prime forms you allow in the product. That's why we never request straight away that the random form that we test for smoothness be smooth with respect to the smaller set of generators. Instead, we allow for all the generators of our sub-exponential factor base to occur in the decomposition. So that's why you have an n here and an n0 there. But what we're really interested is relations that only involve the prime forms of index 1 to n0. So, but if we were to request that they happen just by sheer luck, this would take us forever to find. Maybe it would never happen. So instead, what we do is we're going to first create this relation, and then what we'll do is we'll rewrite every of these elements. So let's say we have an fi here. What we want is to take this ith relation here, and then there's a 1, then there's all zeros, and then there's a bunch of coefficients here. And what it tells you is that fi is going to be equal to a product for j less than n0 of fj to the, for example, if we call this matrix H because it's the HNF, that's going to be I hij. Okay, so we're going to have a way to rewrite every element that occur in the product here. Okay, and then once we're done rewriting, what we have is a relation involving only the index, the fi's where I is less than n0. So that's part of what we're interested in. Now the problem is, once you do that, you do not know if the exponents are large. Now the exponents are always going to be of polynomial bit size. So if you were to evaluate the product with, say, square and multiply, this would be fine. It would all be polynomial time. So we'd be happy, except for the fact that we're interested in those decompositions in the context of isogeny evaluation. And what we're looking at in this context, in fact, the action of a large power of a prime on isomorphism classes of elliptic curves, and that's something that's going to be mentioned in different lectures, then you'll see that this cannot be sped up with square and multiply, which means if we have a large power, then those actions will be taken one by one for however large is the power. So we also want a small vector. So what kind of computational problem are we talking about here? We're talking about finding a vector. So once we have a decomposition, what we want is a vector that is close to it in lambda. So what we have is, let's assume that we have, for example, f equals so product of the fi's to the xi, right? And then let's say that xi minus yi is short for yi in the lattice of relation. Then what we have is that f will also be equal to the product of the fi to the xi minus yi, and the difference is those powers are hopefully going to be small. Okay, if we found a vector that was short enough. So what we're talking about here is finding close vectors in the lattice of relations. Okay, so it's a bounded distance decoding problem, which is in general it's hard. Now, two things. You can try to look at the asymptotic costs with aggressive heuristics, but usually you're looking at dimension being log squared delta. So anything that is exponential in that cost, anything that is exponential in log squared delta is going to be very asymptotically expensive. And every bad approximation factor of the order of exponential log squared delta will make things very bad asymptotically. However, when values are moderate, LLL behaves better than what the asymptotics tell us. It's a sort of a law of small numbers here. And so you can achieve interesting results in practice if the values are small enough. Now, we move on to proving that we can do things in suborders by leveraging the calculations in the maximal order where the discriminant might be very small. So it's a result from Clunas and Pauli. It leverages that exact sequence, which can be intimidating at first, but what we're really interested in is so there is this group here, okay, whose image is the kernel of this map, okay, of the class group, which is bigger. So the class group of minus d, of discriminant minus d, is bigger than the class group of the maximal order. So d being larger here. Now the generators of the class group are the generators of the class of the maximal order and the generators of that group here, okay? And now what we need to calculate, what we want is to calculate the class group of discriminant minus d, which is minus f squared dk, where dk is the fundamental discriminant, the small one. So minus d is large, but we still want relations between those generators because we've seen that this lattice of relation is the key to unlock first the calculation of the class group, but also subsequent problems like decomposition. So the relations between generators of that group are in fact legitimate relations, but also if we take relations between the generators of the class group in the maximal order, which are of the form gi to the di, generated by elements of the form gi to the di equals a principal factor, and then you write that the principal factor here, you decompose it with respect to the generators of this group. What we end up with is an equality. Okay, what we end up with is an equality of the form the product of the gi's to the vi is equal to the product of the gi to the di here, okay? And so if we negate that and we bring it in this side, then what we get is a relation. So we get that the product of the gi to the di times the product of vi to the minus vi, gi to the minus vi is a relation. So, and these are the rows here, okay? So we put the di's here and the minus vi's there, and this gives us another batch of relations. And altogether, they give us a generating set of all our relations. Now, what is the cost of all of this? Well, let's see. So what we have to do is to calculate the class group of the maximal order. So the class group of minus dk, that is one cost. Then we need to know all of the prime divisors of the conductor. Okay, so we need to factor the conductor F. Okay, we have fast factoring methods in L1/3, so asymptotically much better than the class group methods. And then we need to do these decompositions here, which correspond to taking an element and finding powers that with respect to the generators of this group, which essentially means we need to do DLPs in O quotient by P for the P that divides F, okay? So what we have is three components of the cost. Class group in the maximal order, which we hope to be easier because this is the easiest in this field because the discriminant is the smallest. Then factoring F. So what is F? At the worst case scenario, F is about the square root of D, right? I mean, because F squared times D sub k equals D. And then the DLP, so here we're talking about working in FP or FP square, where P's are divisors of F. So here we have L1/3 algorithms for, heuristically at least, for both of these tasks. Why this is an L of D, okay, so this is a much smaller heuristic complexity, so it disappears in the small O's, and this is a something that is smaller than the calculation of the class group of discriminant minus d. So here we win by using this. And in practice, the results are really impressive. So once we apply this Clunas and Pauli method. So in this lecture, what we've seen is a couple of direct applications that have relevance to isogeny computations. And then these will be used in the subsequent modules that are more directed to isogenies. There will be one more module where we'll just open up to what happens in fields of higher degree, so it will be our next lecture. Thank you very much for your attention.